All right, let's dive in. Today, we're going to pull back the curtain on our digital world and look at something pretty amazing, a kind of secret symmetry, a hidden structure that shapes the very nature of information itself. So, just imagine this for a second. What if every single digital code, the stuff that makes our entire modern world tick, had a secret twin? A shadow self that knows everything about it, reflecting all its properties, but in a totally different way. It sounds like science fiction, right? Well, it's not. And it's the core idea we're going to unpack today. So, to really get what this shadow is all about, we first have to get a handle on what a code and its dual actually are. Let's start with the basics. At its heart, an error-correcting code is really just a set of rules. Think of it like this. It takes your information and wraps it in a kind of structural armor. This armor is designed to protect the message from all the noise and glitches it might encounter flying through space or down a fiber optic cable. Okay, now here's where it gets cool. Every single one of these codes has something called a dual code, and this is its mathematical shadow. It's not a copy, it's what mathematicians call an orthogonal counterpart. If that sounds complicated, just picture it as a code that's perfectly perpendicular mathematically speaking. Its entire structure is defined by the original code, but it's completely distinct. And this relationship, this is what's so fascinating. You've got the original code, right? The one actually carrying the message. And then you have its dual, its shadow, whose whole existence is tied to the original. For a really long time, the exact nature of this connection was a huge mystery. Everybody knew they were linked, but how? How were their properties really connected? So for decades, mathematicians were staring at this problem. They knew this link existed, but they needed a key to unlock it. They needed some way to translate the properties of a code into the language of its shadow. And that key, well, it turned out to be something called the weight enumerator. Now I know, that sounds super technical, but think of it like a code's unique fingerprints. Seriously, it's a mathematical expression, a polynomial, that lays out the exact weight distribution of all the code words, basically how the ones and zeros are arranged. It is a complete structural signature. Nothing else is like it. And this is where it all clicks into place. The MacWilliams identities, discovered by the absolutely brilliant F.J. MacWilliams, are the formula. They are the Rosetta Stone. This is what lets you take that fingerprint, the weight enumerator of any code, and perfectly calculate the fingerprint of its shadow, its dual. With this key, the secret of the shadow was finally out. I mean, this discovery was just incredible. But you know how it is in science and math. One huge answer just leads to an even cooler question. And this one was a biggie. What happens when the code and its shadow aren't just linked? What if they're actually the same thing? This very special case is called a self-dual code. It's a code that is its own orthogonal counterpart. It has this perfect, beautiful, built-in symmetry. And it's right here that the story gets even more interesting, revealing a structure that was way more rigid and elegant than anyone ever expected. The next huge leap came from a mathematician named A.M. Gleason, and what he proved was honestly mind-blowing. He showed that these self-dual codes, these perfect mirror image codes, they aren't random at all. Their fingerprints, their weight enumerators, are incredibly constrained. They can't just be any old polynomial. They have to follow these very strict, predictable rules of symmetry. The impact of Gleason theorem was just massive. It took all the mystery out of self-dual codes and showed they were governed by these deep mathematical laws. But maybe most importantly, it built a bridge between coding theory and a field that seemed totally unrelated, invariant theory, which is the study of things that stay the same even when you transform them. This connection just blew the doors open for a whole new universe of research. And you'd think that would be the end of the story, right? A beautiful theory, a new connection. But nope, this was just the beginning. The original MacWilliams identities acted like a master key, and mathematicians quickly realized it could unlock doors they didn't even know were there. So this one breakthrough just kept on giving. Researchers started using these same ideas about duality to solve other puzzles that had been around for ages. They explained these really strange, baffling codes by showing they were actually simple, linear codes just viewed through a different mathematical lens. The theory just kept expanding, from simple ones and zeros to more complex number systems, and eventually they realized this whole code and shadow thing was just one example of a vast universal principle of duality you can find all over mathematics. That simple key had unlocked an entire universe of connections. So, after this whole incredible journey, from a simple question about a code and its shadow, what's the ultimate legacy here? What's the big takeaway? Well, the real core insight is this. The MacWilliams identities aren't just some clever mathematical trick for studying codes. They reveal something profound, a fundamental, mirror-like symmetry in the very fabric of information. They show us that for every structure we build, there's a dual structure out there that reflects it perfectly and predictably. And that really makes you wonder, doesn't it? We found this hidden symmetry in our own man-made codes. So, what other secret dualities, what other hidden reflections and profound symmetries are just sitting there waiting to be discovered in physics, in biology, in all the data that makes up the world around us?